Today we're going to talk about the limit comparison test. All right, so let's recall a sequence. So let's say from n equals 1 to infinity and 1 over n squared minus 1. I think we talked about this one before. And so you see you have the square and you say maybe I can compare it to something and it should converge. We did it with plus, but now with minus. And you see if we wanted to do our limit comparison, just direct comparison test, we'd say, well, n squared minus 1 is strictly less than n squared. So whenever I do reciprocals, I get 1 over n squared is less than 1 over n squared minus 1. So I cannot use this one that by p-series I know it converges to compare this one. So it's not good, but it's just off by 1. Somehow it should work, right? Or what about this other one? So you go from n equals 1 to infinity of 1 over n plus 1. And again, you say this is sort of like the series from n equals 1 to infinity of 1 over n, which diverges. So you say, okay, let's see how can I compare it. So n plus 1 is larger than n. So 1 over n taking reciprocals is going to be less than 1 over n plus 1. And this one I know diverges, but now I have that the little one diverges. Who knows what happens to the big one? So it doesn't help me either. So these two cases are the type that I would just use limit comparison test. And let's just figure out how it works. So the limit comparison test will help you determine when something converges or diverges by taking a limit. All right, so how do you do that? Well, you're going to want to compare to, so you would like to compare to the sum from n equals 1 to infinity, this series of 1 over n squared. So you're going to grab, I guess this is what I wanted. You're going to grab this guy and this guy, just the nth term, and you're going to do a ratio of them. So you're going to say, this color. You're going to say, well, I'm going to take the limit as, you're going to do the ratio. 1 over n squared minus 1 over 1 over n squared, and as n goes to infinity. And in this particular case, if I compute it, I can just multiply this expression by the reciprocal of this number. The reciprocal of this number is just n squared. So this turns out into n squared times 1 over n squared minus 1. As n goes to infinity, this is a rational expression with same degrees, both in numerator and denominator. So the limit will be the ratio of the coefficients. In this case, this is 1. What this 1 tells me is that these two series are going to be growing more or less at the same rate. So that's what that will tell me. Now, let's take a look at what happens here. If I compare it to the one that is the closest to it, but I couldn't compare it with direct comparison, I would do the ratio between this guy and this guy. And actually I wrote them backwards. It doesn't really matter. For the most part, it doesn't matter. So I'll tell you when I write the actual statement, you'll see what I mean. So I'll take the limit as n goes to infinity of 1 over n plus 1. And then 1 over n. And as before, I can just obtain the limit by multiplying times the reciprocal of this number, which is just n. And then again, as above or as before, the limit will be the ratio of the coefficients here. I get 1 as well. Doesn't have to be 1. It just worked out that way because, say, for example, if I would have done a 2 over here, then my limit would have ended up being a 2. It doesn't have to be a 1. My example just happened to be 1. So what does the theorem say? So This is all the procedure you would need to do, but you don't know what this means until I write the theorem. So this works for series that have only non-negative entries or summands. Then if the limit, this is what we did before, as n goes to infinity, of an over bn is equal to L, which is L that is not 0 and not infinity. So in our case, L was 1. That's good enough. Could be 2, 3, whatever you want. These are ratio positive numbers are going to be positive, but we don't want it to be 0 or infinity. If that's the case, then we have that the series of the ANs, n equals, I'm going to start them at 1, but could be starting anywhere, and the series of n equals 1 to infinity of bn, both either converge, so they have the same behavior, or both diverge. So if you know that one converges and the limit is not 0 or infinity, then you know that the other one converges, and the same for divergence. So back to our two examples, you see we knew this one converges, and we knew this one diverges. Then we went ahead and did the ratio of an over bn, and the order didn't matter, as I said, because the limit is not 0 or infinity. You see, the only way the order would matter is if, or the order you put them is if the limit goes to 0 in one order and goes to infinity in the other, plus minus infinity, let's say. But if it goes to 1, if you do the reciprocal as 1, say the limit went to 2, the reciprocal will be 1/2. At that point, that is not going to change the conclusion of the theorem that says that both converge or both diverge. So since the limit is 1 on each one of these, I know that since this one converges and they have the same behavior by the limit comparison test, this one will converge as well. Now, this one diverges. Since my limit is not 0 and not 1, not infinity, it's 1, then I know they have the same type of behavior, and since I know this one diverges, then this one diverges as well. So you see, this is definitely more powerful than just your regular comparison test. Then you have to address the cases of the infinity and 0. So what happens? So let's say that 1 again, 2. So what happens when you have that the limit as n goes to infinity of an over bn, if it goes to plus minus infinity? Well, they're positive, so it's just going to be positive infinity. My apologies. Well, here, what that's telling you is that the series of the ANs is growing at a faster rate than the BNs. So here what I'm going to say is that if this goes to infinity, and since this one is growing faster than this one, and if this one diverges, then I have that the ANs also diverge. Because at that point, your limit is telling you that the ANs are growing much. Oh my goodness, I wrote BN. Did I say AN? I think I said AN. You see, if I were like an honest to goodness YouTuber, I'd tell you, write out that in the comments below so I can get, interactions. Anyways, so that's telling you that the ANs are growing much faster, but you already know that the BNs diverge, so the ANs also diverge. All right, so that's that. Or maybe, well, they can be decreasing, so I'll tell you it's not decreasing as fast, let's say. Anyways, that's just what that statement would give us. Now, if the limit as n goes to infinity of an over bn happens to be 0, then you know this one is growing even slower, or it is decreasing much faster than this one. So if you know that this one is going down to 0 faster than this one, and you know that the sum of the bn's converges, what did I write there? N equals 1 to infinity of the bn's. If this one converges, then you know, okay, it's late today in the weekend, so I apologize, must be tired. Um, then the an converges. So I think we can do a few examples and then wrap this video up. Okay, so let's start with something that looks like a geometric series. So n from 1 to infinity. This one you can start at 0. Let's start at 0. Why not? That's geometric looking like. So I don't know, 3/5 or something like that. So 3 to the n, but let's throw in a plus. So that is a little bit larger, quote unquote, than my uh geometric. Although yeah, this is silly. Let's add 2, because really I could separate this one out. Let's do 2 to the 4n. This one is silly. I don't need the limit comparison test because I'm unhappy with my example. We're gonna solve it with a limit comparison test anyways. But you could also write it as 3/4 to the n by separating that quotient, plus 2 times 1/4 to the n. And you know, because this number is smaller than 1, this series just with that term converges, and then you know that this one converges because it's a number less than 1, and then you just the sum of them converges as well. Not that nice, but oh well. I mean, it's just it's okay, but it's just something you don't need the limit comparison test to solve. Just with the geometric series test suffices. Anyways, but just for the sake of example, we're going to compare it to n equals 0 to infinity of 3/4, and I write 4/3, 3/4 to the n. Because I know by the geometric series test that this one converges, because 3/4 is less than absolute value 3/4, if you want, is less than 1, right? Therefore, by the geometric series test, you have that it converges. So now I just have to do the ratio of the coefficients and take a limit. So limit as n goes to infinity of 3/4 plus 2 over 4 to the n over 3 to the n over 4 to the n. I'm going to split it because it's going to be more convenient to do it that way. And often these ones you're just not you're always, but very often you're just be multiplying times the reciprocal of the denominator. 3/4? Oh my goodness. It's late in the day. 3 to the n. I typo there. Sorry about that. I'm acting as if I don't do that often, but okay. Just let's pretend. So I'm gonna be multiplying times the reciprocal, so 4 to the n, and then 3 to the n. And let's see what happens here. So you see, firstly, the 4 to the n will cancel right away. And then this is going to be the limit as n goes to infinity of 3 to the n plus 2 over 3 to the n, where you can distribute this and write it as limit as n goes to infinity of 1 plus 2 over 3 to the n. As n goes to infinity, that exponential function 3 to the n goes to infinity. The 2 is fixed, so you have a fixed number that is divided by something that goes to infinity. This term is going to be going to 0 because the denominator is going to infinity and the numerator is fixed. So you know that's going to 0. So your whole limit is going to 1. Therefore, you can compare it, and using the limit comparison test, we have that the series from n equals 0 to infinity of 3 to the n plus 2 over 4 to the n converges, because we had that the geometry we compared it to, which was just this chunk. Oh, that was such a fail. Um, oh my goodness, I need one more. So just this chunk, let's say, that one converged. So that's one example. Let's do another one where you have a function that we want it to go down to 0 somehow. Let's do something like, let's start at n equals 2. Let's involve a natural log somehow. Um, so for example, natural log of n over n. So let's see how we do with this one. By the way, I should have moved it a little bit lower. There it is. So let's see how we do with this one. So, okay, so you have a 1 over n. Should that in of itself seems like it's going to diverge. So, because n equals to 2 to infinity of 1 over n, you know this one diverges. Oh, this is a silly one because the natural log, oh, the natural log, never mind. This is a good one because the natural log of n, no, it's a bad one. Natural log of n is going to be larger than 1 after, for example, after n equals to 3, the natural log of n is already larger than 1. So this is larger than something that diverges. So the direct comparison test would do it. So my examples today are not the best. I started with really strong ones, and now that I'm just writing them on the fly, not the best, but nonetheless, let's figure out how this one goes. So you're gonna grab your ANs, and you're gonna do the ratio with the BNs. Wrong color. With the BNs, and you're gonna take the limit as n goes to infinity. Now, if you wanna save yourself some time, like in this case, you could, for example, do natural log of n over n, and then just multiply times the reciprocal of that one. So that this would be this term. And then for the red one, you can just do your n, which is going to be the reciprocal. No, that's not what I want to do. That's going to be the reciprocal of this term here. You can multiply times the reciprocal right away if you want to save a little bit of time. If you feel uncomfortable and you think you're going to make mistakes, just divide by an over bn and you take it from there. All right, so, but in this particular case, you can see that the n's will cancel. So that's going to give you the limit as n goes to infinity of natural log of n, which happens to go out to positive infinity. So now, in some textbooks, they'll tell you, well, at that point, you don't know. But you do know, because you see, we're in this case where the an over bn goes to infinity, but bn, so let's identify who is an in our example and who is bn. This is going to be the sum of the ans, because that's the one we put in the numerator, and this is going to be the sum of the bn's. So it said, the statement, if you go back, rewind for 1 second, it said that if the limit is infinity and the sum of the bn's diverges, then the sum of the ends also diverge. So you see, some books will tell you, oh no, if you got infinity, you cannot do anything, but it's just you have to be a little bit more careful and know what what you really are doing. What the limit is telling you is that this natural log of n over n is growing faster, or is decreasing much slower than the 1 over n. So if this one diverges, yeah, this one will diverge as well. So by the limit comparison test, we have that the sum, oh, don't have room. Well, I can write it here. From n equals to 2 to infinity of natural log of n over n diverges. Now, as I said before, we could have used direct comparison for this one. Not the best example, but the mechanics of it is of the solution. The mechanics are exactly the same. And I'll be honest, once you know the limit comparison test, I would always use that instead of just doing direct comparison. Just because direct comparison sometimes will work, sometimes won't, but the limit comparison test will work, period. So as long as you're choosing the right thing to compare, of course. But anyways, that's what I had to say about the limit comparison test. I will stop here, and I thank you for watching, and I'll see you in the next one.